Hello. Wednesday, people. Today's Wednesday. Is that right? I get confused. Like, I know when it's Friday because I'm here and it's Friday, but today is Wednesday. I'm here. It is me, Daniel Schiffman, for a bonus Coding Train live stream. Now, before you get too excited about this bonus live stream, here's the thing. I had a regularly scheduled live stream last Friday. We could probably open it up here on my computer and find the YouTube video where it said neural networks continued. And as I recall, I spent some time improving the matrix library, and then I talked a bit about a feed-forward algorithm, and then I started to implement that code for the feed-forward algorithm in a neural network class. And then I went home and I had a sip of some herbal tea and I read a book quietly and, I don't know, painted. I don't know what I do at home. It's a lot of chaos, actually, really. It's like running around and taking care of children. But that's like what I like to imagine that I was doing. And then at some point, I had some conversations, I reviewed some video. It seemed apparent that even though it can, oh yeah, I gotta talk about the haircut thing. Yeah, okay. Even though often what is most useful, I hear from my videos, is when I make mistakes and I have to debug a problem and sort something out. What I'm learning, I believe, and I'm not 100% sure about this, but my sense is that's particularly useful when I'm actually coding something and running into errors in the code, and I have to go back and fix those errors and find those errors, because that has some real pedagogical value. However, when I am taking the time to teach about a particular formula from a math algorithm and diagram something on the whiteboard, and for large portions of the video I have it completely wrong, and then I go back and erase and fix it, that edited down sometimes doesn't read as well. So today's bonus live session, which a bonus is hardly a word to use now, is just to simply revisit that tutorial about the feed-forward algorithm. Let me actually open it up. So let me go here and find what I'm looking for. So in case you're wondering what I'm referring to, here I am on the Coding Train YouTube page. These two edited videos came out from this live stream, and the rest have not yet, because if I go to...
Good morning, Internet. It is...
Whoa. You can really hear an echo in the music. Anyway, that's another problem. I need like a secret monitor in my ear or something so I can listen to the music that I play without having it play out through the speakers and into this microphone. Or I just need less delay, because there's a delay. Wait, actually, I could probably, anyway, sorry. Wait, I was doing something. I'm gonna go to Show More. And you can't even see what I'm doing. I'm gonna go to Show More and look here. Feed-forward neural networks part 1. Let's click there.
All right, I'm back.
Okay, I'm gonna mute myself. I'm going to put myself at 2 times speed, and I'm going to leave this running behind me, and I'm going to keep talking. So this is the part, I'm going to try not to look at it. Maybe this is very distracting for you. So there's one little problem. You might notice Wilderness Dan, who was trapped in a forest, living amongst the trees for months only with machine learning textbooks to read, came back to civilization, went and got a haircut. So Wilderness Dan also moves really fast gestures. So there's going to be a little bit of a continuity problem because I can't recreate that outfit and hairstyle, but life will go on. So yes, if you're looking for, I was trying to think of a different way to say drunk Dan, inebriated, watch it 0.5 speed. Okay, this is too distracting for me. So this is my main goal for today, is to revisit this video. It is approximately 2:15 p.m. Eastern time right now. And I'm hoping this is going to take about an hour. And then I will be on my way, and I will be back this Friday to continue. And this Friday, if all goes well today, and I can get these other videos out, this Friday I will do backpropagation and training. Well, that's the same thing. I'm going to do the backpropagation algorithm. And then I will do, hopefully, some coding challenges that involve using the neural network library. So the coding challenges will be kind of standalone videos that make use of the library that's built. So without having to code up all the neural network stuff in the coding challenge, I can just make use of it. That's my current thinking right now. So I'll probably do, I mean, I kind of don't want to, but I would probably do MNIST, maybe XOR and MNIST as these kind of basic demonstrations. All right. What else can I say? Use a fake beard. Oh, I wish I had a fake beard and wig to wear. That would be awesome. Okay. So whiteboard is here. Now, one thing I would like to do, because this is going to be a video that heavily makes use of the whiteboard, let me make some marks here to figure out. That's the top. You can see the tip of my finger. The rightmost edge that you can see is about here. So let me put something here, okay? That's the rightmost edge. I don't have to worry about the leftmost edge because I'm not really going to walk back here. And then the bottom is about here. And let me put a mark here. Okay, so I have mostly marked off where my area is. And when I draw over here, you can't see me. Which I guess is fine. I will try to like stay here as my leftmost. Okay, so that's good. Are there any questions? Or let me actually pull up. Oops, I'm in the wrong screen. I was thinking of pulling up. No, I guess I'm just gonna get going. Look at the chat. Anything I'm forgetting? Oh, I guess I could mention. I don't need to mention all that stuff. People in the chat are telling me that you can see the down mark. Is that really a problem? Does this really ruin your ability to enjoy and learn from this video that you can see a red mark here on the bottom? Have no fear. Don't worry. I've got you. I hear you out there, internet. I'm listening. I will write the mark a little bit lower and just have a sense of it, that it's there, but really a little bit higher. And maybe now that mark is invisible to you and you'll be able to go on with your day happy, full of delight, and without a care, carefree, and into the snow to frolic and be, because there are no marks that you can see that might affect the way that you can absorb this material. All right. All right, here we go. I guess I feel weird just getting started, but I'm just going to get started. I'm looking in the chat. Oh, Kay Weekman is pointing out a flaw in my design system. It's not as bad as a flaw that leads one to, by accident, issue a missile alert, but that I should put marks in the corners. That might actually be helpful. So let me find the corner. It's about over here. Oops, no. Here, here, here. Maybe this is the corner, about there. And then the corner down here is about here. And I think I'm not going to worry about the corners over here. All right. Although I should give myself a height mark over here, which is going to be right about there. Okay. Ah, then the camera went off. Perfect timing. I am soon going to investigate that Magic Lantern firmware stuff. But I feel like this is part of my life now. If I didn't have to press the button every 30 minutes, like, who would I be? How would I get through the world and interact with the air and space around me? The other thing I'll say is it's a balmy 76 degrees Fahrenheit in this room. I filed a work order to have the climate control system of this room looked at, and I received confirmation back that the work order was complete. And yet, it's quite warm in this room, so I'm going to have to make another attempt, and hopefully on Friday I'll have my nice cool room, so I can start wearing my, all my wonderful sweaters that I want to wear for you on the internet. I always have to be in the t-shirt, et cetera, et cetera. Okay. Yeah, no, the camera turning off thing is terribly annoying. I need to get that fixed. I'm really just joking about how it's like a part of my, that'll only be a good thing. I shouldn't get too stuck in my ways. All right. It does keep me awake, though. All right, so let's see how this goes. Let's see, I need to have this. Okay. I think I'm just going to begin. I'm ready to do this. Why not? No time like the present. By the way, this 3 blue 1 brown channel is so good. I mentioned that already. It's so good. It's so thoughtful and careful with all this design and animation. It's amazing. I aspire someday to, I guess what I do is just a totally different thing, but yeah. All right. Okay. I'm trying to decide which camera I should start with. It's really going to all be on the whiteboard. I do need to have the matrix class available, but do I want to reference? I think I don't need to reference the continuity problem because it won't really become apparent. This is sort of like a new part, so it makes sense that it would have gotten a haircut. But once you get to the next part, it won't have made sense anymore. I could always redo the next part too, but I don't think I need to. Let's just go. Let me just do this. Forget about the continuity thing. We'll address that later. I'm standing in the wrong camera feed. All right. How did I start my previous one? I started over on the whiteboard. All right, we'll do that. All right, this is a momentous occasion. I got a haircut from the last video, if you might have noticed. I said I wasn't going to mention it, but I mentioned it. And what I'm actually going to do now is describe, we finished off, I mean it's not finished, we're going to have to do more, building this little matrix library that's going to allow us to do some math stuff that we're going to need when we implement the code for this particular video, where I'm going to describe the feed-forward algorithm of neural network. Now, I want to give thanks to 2 sources that I've used primarily in the sort of studying and preparation for this video. Number 1 is Make Your Own Neural Network by Tariq Rashid. You'll find a link to this book at the Coding Train Amazon shop in this video's description. And also I want to thank and reference the 3 blue 1 brown channel, which has a playlist. I forget what it's called, but there's a video called What is a Neural Network? At the time of this recording, there's about 4 videos. Those are amazing. They're animated, they're thoughtful, they're careful, they're really, for understanding and having an intuition for how a neural network works, and for seeing all the pieces of an algorithm, I highly recommend those. What I'm really attempting to do in my videos is sort of figure out a way to implement a lot of the stuff that's in this book and those videos in code. So in this video, the next video I'm going to start working on the code. This video I'm really going to talk through the algorithm in my own words as it applies to where I am in this playlist. I'm spending way too much time introducing this video. Let's just get right to it. Okay, so where I last left off before I started working on matrix math stuff, I had built this simple example of a perceptron. And a perceptron, the idea of a perceptron as a single neuron that receives inputs. So we might have inputs, something like x1 and x2. And those 2 values go into this perceptron. They are processed, and then some output is generated, often referred to as y. So this is the thing that I built last. I talked about some of this in a previous video, but I need to kind of just rehash it again to set the stage of where we are. So let's say we're trying to solve a simple problem, like understanding logical and. So the inputs that into this system, this learning system, this simple perceptron, can be true or false, or true or false, or we could also think of that as 0 or 1. Right? And we want this perceptron system, this system, to output a 1 for y only if both the inputs are true. So we could say if both the inputs are true, then we want to get a 1. You know, if the inputs are true and false, we should get a 0. If they're false and true, we should also get a 0. If they're false and false, we should also get a 0. So this is the kind of system. Now, the thing that I talked about, so this is great, exciting. Wow, we have a neuron. It can receive inputs. It can boom, it could give me outputs. All is right in the world. The problem is most problems in life are more complex than this very simple scenario of two inputs, each only a Boolean possibility, and an output solving for a logical AND. So, for example, let's just make this slightly more complicated. Let's take this idea of something called XOR, exclusive OR. So if I were to switch this, and I need an eraser, here it is. If I need to switch this to OR, this would now be the desired outputs for OR, right? As long as one thing is true, that's what we've got. Exclusive OR means we will only output true if one thing is true and one thing is false. So this, for exclusive OR, will actually output a 0. And I talk about this more in a previous video, this is not a linearly separable problem. We can't graph the solution space and draw a line right in the middle and say all the answers for true are on one side, all the answers for false are on the other. So this is where this idea of a multi-layered perceptron comes in. Most problems, as I get further and further through this playlist of doing more and more things, cannot be solved with a single neuron, this idea of a perceptron. This is where what happens to solve a problem like XOR, if we add a second neuron and send those inputs, the same inputs into that neuron, and then set the output of that neuron into the output here, now we have what's called a multi-layered perceptron. Just pause for a second. Okay. Now this is typically referred to as a 3-layer network. And one thing that I'm going to do right now is, even though one of the first problems I'll try to solve once I build a neural network library is this XOR problem. In order to demonstrate how the feed-forward math works, it's going to be clearer, I think, if I have a different number of inputs than the number of hidden nodes. I said, let me go back. Time out. Okay. Hold on. Yeah, everybody's telling me 2-layer. So hold on. I've seen this before, and here's my feeling on this. I said this previously. Yes, this is kind of 2-layer. Maybe I should say, because there's the hidden layer and the output layer. The inputs aren't really a layer. But I like to think of it, am I wrong? Let me look this up. I like to think of it as 3-layer and the inputs being like a special case layer. But let's say 3-layer network. Okay, how about 3-layer neural network? See, so that's the question. This input layer, so I think that it's reasonable for me to say 3-layer. It is called a 2-layer network. But, okay, so where are these sources coming from? Oh, 2-layer network. Okay, you're right. Let's visit this page. A 2-layer network, 1 hidden layer, 4 neurons or units, and 1 output layer with 2 neurons. Right, a 3-layer network. Okay, so I better say 2-layer. Well, okay, it's 5 layers. Yeah, all right, so it's a 3. Oh no, but somebody in the chat said, we could have this discussion. I'm going to go back. I'm going to start this little section over after I took my break to blow my nose. This is what's known as a 2-layer network. Sometimes I like to think of it as 3 layers because I count the input as a layer itself. Input layer, hidden layer. I said hidden. See, I didn't want to say hidden yet. What am I trying to? I lost my momentum here. I'm gonna explain this one more time, then I'm gonna keep going. Where did I really last leave off? Okay. Yes. This is what's known as a multi-layer perceptron. We have this output layer. This you could consider an input layer, although the input functions differently than these other 2 This is a layer, this is a layer. And here's the thing. This is called a hidden layer. The reason why so I'm going to say hidden is right here. This is input right here. And this is output. Now, as I get further and further through many videos that I hope to make and examples I hope to make, we're going to see that there are many complex architectures for how you might diagram and design a neural network system. This is a very, very basic beginning point. And typically this is a two-layer network, a hidden layer and an output layer. The input isn't really considered a layer, although I sometimes do it. So I like to call this a three-layer network, and we could get into some we could have a comment thread about which is precisely correct for this. Someone start that comment thread, and then I'll learn. But let's just call this a two-layer network. The reason why, incidentally, this is called a hidden layer is because we, as the operators of the neural network, right, we are going to give the neural network data. We're going to say, hey, take true and true, or take true and false. So we're really here interacting with the input. We also want to see the output. We want to take the output and use it in our project. Oh, you gave me false? Thank you. What's the answer? Hidden are the pieces that exist in between where the inputs come in and the output comes out. And this is kind of the magic, as we'll see as I get further and further along in solving different kinds of problems, how this works. Now, the main purpose of this video, even though I'm being very long-winded about it, is to talk about the feed-forward algorithm. What happens to the data as it comes in, passes through, and exits through the output? And in order to describe the math, what I want to do is add one additional input, x3. So I'm going to add that, and that will also go into this hidden neuron and this hidden neuron. So now you can see we have 3 inputs, 2 hidden nodes, and 1 output node. And all of this is totally flexible. If you've ever looked at that classic sort of hello world machine learning problem where you have this data set of handwritten images, often the inputs are 784 for 784 pixels. And the outputs, there are 10 outputs because you have a probability for whether it's a 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. So the design of this, how many inputs, how many outputs, how many hidden nodes, how many hidden layers, this is all food for thought. But I just want to look at this very basic 2, maybe this is 3, I think. It's a 2, it's a 2, 2. Okay. It's a two-layer network. Deep breathing, deep breathing. It's going to be fine whether I say 2 or 3, life will go on. Now, you might be wondering, weren't you just making all these videos about matrix math? How is that relevant here? Well, it turns out that the math for what each one of these nodes do is something called a weighted sum. What do I mean by that? These are all connections. Each input connects to each hidden node. Each hidden node connects to each output node. These connections all have a weight. And in fact, if we call this H1 and H2, right? This is hidden 1, hidden 2. We can have weights between 1 and 1, and 1 and 2, and 2 and 1, and 2 and 2, and 3 and 1, and 3 and 2. So those weights, right, if there are 3 inputs and 2 hiddens, there's actually a weight matrix. There are 6 weights. There are 6 possible connections. And I could write that like this. I could say weight between 1 and 2, weights, this is where I practiced this so many times. This is the part where Dan messes everything up. I don't think I messed it up yet so far yet, but I just wanted to think about this for a second. It's called wait, okay. Row, column. I totally messed this up. So let me write out the weights in a matrix. So if I have a matrix that's a row column, I can have row 1, column 1, row 1, column 2, row 1, column 3. Row 2, column 1, row 2, column 2, row 2, column 3, right? So I have row 1, row 2, columns 1, 2, 3. So So this is a notation for writing all of these weights. Now, let me now label the weights in this diagram, and I'm going to do it in a particular way. I'm going to say that this is a connection between hidden 1 and input 1. This here is a connection between hidden 1 and input 2. This is a connection between hidden 1 and input 3. And here I have a connection between hidden 2 and input 1, hidden 2 and input 2, and hidden 2 and input 3. You might want to pause this video, just take a look at this, and take a look at this, and see if it makes sense for you. The point of what I'm saying is, what should be intuitive or sort of like feel somewhat normal is like, okay, there's all these connections. There's connections 1 and 1, 1 and 2, 1 and 1, 2 and 1. Ah! It's so hard. Let me do it. There's connections where hidden 1 is connected to 1, 2, and 3, and hidden 2 is connected to 1, 2, and 3, right? And so here are all the weights from inputs 1, 2, and 3 that are connected to hidden 1, 1, 2, 3. Here are all the weights that are connected to hidden 2 from inputs 1, 2, and 3. So why am I spending all this time driving myself crazy and incidentally driving you crazy, spending all this time trying to label these and do this matrix? The reason is the value, the math that I want to process here in the hidden node is the weighted sum of each input multiplied by the weight added together. So let me give myself a little bit more space here on the whiteboard and say that what I know that I want to end up with is the following. I want to end up, I've got to give myself a little more space here. Hold on. I should just pause here. It's actually the right way. Yeah. I know what I want to end up with is this weighted sum. So let's look at that weighted sum. First, I want to take this weight 1, 1. Oh, hold on. Give myself some more space. I wrote it in the middle. I want to take this weight 1, 1, and multiply it with this input. Weight 1, 1 times x1 plus what now? This weight 1, 2 and this input plus this weight 1, 2 times x2. Then I want to take this weight 1, 3 and multiply it by x3. 1, 3 times x3. And you can see how this looks nice and neat. The weight 1, 1 goes with x1, weight 1, 2 goes with x2, weight 1, 3 goes with x3. And we can do that same weighted sum for all the inputs and their weighted connections to h2, to hidden 2. And that's going to be weight 2, 1 times x1 plus weight 2, 2 times x2 plus weight 2, 3 times x3. This is the result that we want. And I could have just basically done all of this without thinking about all this notation and matrices with a for loop. Because I could just say like, oh, I have an array of inputs, I have an array of hidden, and then I have an array of connections, and then I'm going to do some for loops to multiply all the inputs. But the reason why I'm spending all of this time doing this is that look at something really interesting. This might look familiar to you if you've been watching the previous 3 or 4 or 5 videos about matrices. What is this really? This is the matrix product of this weight matrix and a column of inputs. If I put this right here, x1, x2, x3, and I write a big X there for matrix product, or I could put a dot there. Maybe a dot would be a better notation for matrix product. We can see here that, remember what that matrix product is? It's this row multiplied, the dot product of this row with this column. 1, 1 times x1, 1, 2 times x2, 1, 3 times x3, all added together. And then the next is this row times this column. So it just works out perfectly. This is why matrix math is so relevant and is used in all of neural network deep learning implementations, because the way that the feed-forward algorithm works, and mind you, there's a lot more to the feed-forward algorithm that I need to talk about. I haven't talked about the bias yet or the activation yet. There's more, but I just want to get now to this primary understanding of The inputs come in, we take a weighted sum of all the connections between the inputs and the next layer, and that can be done in a single operation if in our code, the way we implement it is we store all the weights in a matrix and all the inputs in a matrix. The weights are going to be, the inputs are always going to be in a single column. And actually that could change based on the design of your neural network, but in this case, that's how that's going to work. Okay, I'm going to pause for a second. Oh yeah, dot and cross products or something else. That's a good point. Okay, so now the question becomes, so far I feel like this is an improvement off of what I did on Friday, where I got all the notation wrong constantly and continuously. I need to go through the activation stuff and the bias stuff. The question is, does it make sense to actually break this up into multiple videos? Like, should I actually have should I wrap this video up and have the next one go through activation and bias, or should I just keep going? What should be the symbol? Oh, the train. I'm just looking at the chat. Okay. That's excellent. We're up to 77 degrees in here. It's getting warmer and warmer with my moving around so much. Keep going. Oh yeah. No, okay, I'll keep going. Yeah. I just like, is anyone keeping track? How much time do you think that was? You know, obviously there were like several minutes in there when I like pausing when it gets edited. One video. Everyone's saying, all right. Mathieu is asking, how long do I think the rest will take? You know, 15 minutes? Yeah, that's what. So let me keep going. I think it makes sense to be in one video. I started 18 minutes ago. There's probably at least 3 minutes of editing there. All right, I'm going to keep going. We can always, yeah, let me keep going. I'm being told from the live chat that's going on that the dot really means something else and the cross product is something else. So we're just going to put our symbol for matrix product will be like a nice little, you know, steam engine train thing. Okay, that aside, what else do I need to do? So we've established this beginning part of the feed-forward algorithm. The inputs come in, the weighted sums get added all together inside these hidden nodes. Now there are two big components that I've missed. Let me just write this over here. One is a bias, and two is an activation function. I'm kind of not sure which order to talk about these things. But before I do either of those, actually what I think I want to do is take this formula and break it down into something much smaller. So what if I think of this weight matrix as just a big capital W, and then I take I need a symbol, I can't draw a train here, the matrix product between this and the inputs, right? And so the hidden layer, and so we can think of this as hidden is a column, so that's really J, right? Hidden J equals weights, I, rows and columns, times inputs J. And when I say times, I mean matrix product. So this is me rewriting this, because this here, if I give myself a little space, is really like what I'm doing here is I'm calculating H1, H2, and H2. Whoa, 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 whoa. I got that wrong. Let me go. It is a regular dot product. All right. Hold on. Let's just go back to where I was here. Because it's not, I see this as a column. But duh, it's it's one column. It's a 1. It's a 1 there in the column spot. It's row. Yeah. Okay. I was doing so well. I'm a very flawed person. Okay. Whew. There was a time. I think there was a time in my life where I was really good at this sort of stuff, and I don't know. I just left. It left. I'm trying my best. Okay. All right. But before I get to the bias and activation, I think what I want to do is rewrite this. Hold on. Okay, before I get to the bias and the activation, what I want to do is rewrite this as a smaller formula. So I want to consider the weight matrix, for example, just as the capital letter W. And I can think of it as a matrix of I rows and J columns. I and J are kind of terrible because they look so similar, but the weight matrix of I rows and J columns. Now, we're taking the matrix product, which I'm just going to use a dot here. I think that's going to be fine. The matrix product between this and the inputs. Now, the inputs is a matrix, but it's one column, but I rows. And the point of the reason why I'm doing this is because I'm trying to get the outputs. What I want is I want to know what number to send out of here. The data's flowing in. We get this weighted sum. What number flows out of there? And the number that flows out of there I'm going to call the hidden. It's really, I'm trying to get the output of H1 and H2. So the outputs of the hidden layer, just the inputs are the inputs to the hidden layer. The outputs of the hidden layer are the inputs to the output. A lot of inputs and outputs there. But the previous layer sends in the input. So whatever comes out of the hidden goes in here into the output. So hidden I equals the matrix product between the weight matrix and the inputs. But there's more. So what are the things that I'm forgetting? And I can actually fold these two things in right in here. The things that I'm forgetting are, one, the bias. So if you recall, when in some of the previous videos that I've done that looked at linear regression and the simple perceptron, is that correct that I talked about bias in the linear regression video? In some of the previous videos, such as in the previous videos where I went through the perceptron, for example, remember I was trying to find this line and what points would be above it or below it. And I've got to really deal with the problem that all the inputs could be 0. If all the inputs are 0, then the weighted sum is always going to be 0. That can't be right. So we need this bias. We sometimes need to make it easier or harder for it to, so to speak, fire. Like we want to bias the output in a given direction. So one thing I would write here is I would also say plus that bias. So, and that is a single column vector as well. So really, if I'm down here again, and boy am I running out of space, but that's okay, I would do this matrix product, and then for every single one of these hidden, I would have a bias, B1 and B2. Right? So there are weights and bias. And by the way, it's perfectly legitimate to ask the question right now, well, what are the values of the weights? What are the values of the biases? This is what I'm going to get to. I just want to understand the algorithm. The whole point of this sort of learning system that we're going to create is to figure out how to tune all the values of all these weights and biases so that the outputs match up with what we think they should be. The system needs to somehow adapt and learn and tune all those values to perform some sort of task. And in a sense, this is really just one big function. That's why a neural network is often called a universal function approximator. It's just a function. It's just a function that receives inputs and generates an output. That's a function. And we have to, in theory, if we have enough of these hidden layers and hidden nodes, there's no inputs we couldn't match with some given set of outputs. So anyway, we're going to get to all of that. But I'm back here, so I need to add the bias in. And then there's something else. You might remember from the simple perceptron example that we had this activation function. Whatever this weighted sum plus the bias would be, if it was a positive number, we would turn that number into +1. If it was a negative number, we would turn that number into -1. And this is something that's very typical of neural network-based systems. Whatever these weighted sums come in as, we want to squash them into some known range. And there are a variety of different mathematical functions that can do this. And while this is not typically the sort of latest and greatest and most cutting edge activation function, the function that is we will find in a lot of textbooks and early implementations of neural networks is something called a sigmoid. And sigmoid is a function that actually looks like this. F of x equals 1 divided by 1 plus e to the negative x. I'm not 100% sure I got that right. Let's go look at the Wikipedia page for the sigmoid function. Yes, Simon, I did see your image about the bias. Thank you. Okay. So hold on. I'm coming over here to sigmoid. Let's go to the sigmoid. Oh, wow. I actually got it right. Okay. Whoops. Oh, this camera went off too. All right. People are telling me the index should be J. For, hold on, let me just look. Should be J for B and H. I don't think so. I really thought about this. Right? The row is I, the column is J, the column is 1. The row is 1, 2, 3. The row is I, the column is J. 1, 1, 1, 2, 1, 3. Am I wrong about that? Oh, I'm in the wrong, totally in the wrong camera. Right? The row is I, column is J. So this is really row 1, 2, 3. I mean, sure, if I made it an array, because it is a flat array ultimately, but I'm going to, in my implementation, actually have it be a column matrix. Because you added the bias, the left and right side of the equation, wait a sec. Oh yeah, that's bad. I will fix that. Yeah. Okay, K Weekman. I would like to hear from K Weekman in the chat if it's okay that I'm using I. Or am I going to get flamed in the comments like I will about my 3-layer network? Oh yeah, whoops, this is kind of messed up. Thank you, I'll fix that. Well, you guys are way behind me. Oops. All right, so hold on. So the Dexis, yes. See above. I don't understand above. I underscore J and a summation. Yeah, thank you, Simon. I will draw the bias in at some point. That's a good point. I need to sum over J, and it's I underscore J. So because these are really this, right? So aren't I summing over I? 1, 2, 3, J is constant. But I mean, oh, because I'm taking the J of here and applying it to there. I see. I see. I see. God, notation is like the worst thing ever. I need some milk. Okay. Yeah. 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 Right. 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 Apparently not. It would help. Yeah, all right. I'm just going to keep going. I'm gonna do my best here to keep going on. I'm going to go on. Okay. The thing I was talking about, I was coming over here to talk about sigmoid. When I come back, I'll fix some of that stuff. Okay. Okay, so here we can see I did get the correct formula for the sigmoid function. What is this number e? E is called the natural number. It's the base for the natural logarithm. It's like 2.71 something or other. It's sort of one of these magic numbers. Euler's number, you can read up about it. But and to be honest, the sigmoid function is barely used anymore in sort of modern deep learning research. But I think it's a good starting point for us to look at and understand why. And in other videos, I will take a look at other activation functions. But the reason why the sigmoid function is used is because it takes any input, any number, if you pass it through the sigmoid function, you will get a number between 0 and 1. And so this is perfect for a lot of scenarios. It takes this input, it squashes it, so higher numbers are going to be much closer to 1, lower numbers are going to be much closer to 0, and the bias is going to can push things closer to 1 or closer to 0. This squashing of it, it works really well because you can kind of, we can get a sort of true or false, 0 or 1. We can get a probability value between 0 and 1 when we get to the output. Lots of possibilities. So this is the and it's sigmoid function. So, so I'm over here, by the way. I need to correct a couple things. Where's that eraser? Number one is I kind of did something horrible here because I made these equations not equal to each other anymore when I was talking about the bias. So let me not put that over here. So, okay, another thing I want to mention is I'm kind of fumbling here with these index values. What we're really doing is the matrix W is rows and columns, so I and J. The input is a single column vector, but we're still iterating over I because the I of the weights gets multiplied with each row, which is now I of the input. So, the exact notation aside, the point of the feed-forward, the truth of the feed-forward algorithm is the inputs come in, you take a weighted sum, you add in the bias, you take that weighted sum, add the bias, pass it through the activation function, and that result feeds forward towards the network and goes straight to the output. And guess what the output does? The output takes, the weights of all the connections between the hidden and the output. So the matrix product of the hiddens with those weights plus its own biases, these are different biases, these are the biases for this particular, the output node, and then passes that through the sigmoid function as well. So this just happens with every single layer. Here come the inputs, weighted sum, passes the activation function, send that as output into the weighted sum of the next node, pass through the activation function, send that as output, et cetera, et cetera. I was getting the question and it was being pointed out that I didn't draw the bias anywhere into this particular diagram. So a nice way to draw the bias into the diagram is to think of it as another input at each layer. So for example, if there were always an input that had a value of 1 that connected like this, now we have bias 1 and bias 2. So these are like weights that are getting weighted with an arbitrary input of 1 that's always coming in. And the same thing with here. Now we have also another bias that's coming into the output. So at each layer there is a 1, which its weight is like this bias. There's only 1, so B1. So you can think, you'll often see, I could probably pull up a much nicer diagram. Again, highly recommend you go watch that. You should have just been watching the 3 blue 1 brown video all along, if I'm being perfectly honest. But this hopefully gives you a sense of what the pieces are. The point of me doing this, in a sense you could just skip ahead to the next video. In the next video, I'm going to I have a matrix library which does this matrix math. I can add two matrices together, element-wise. I can perform a matrix product. I can apply a function like the sigmoid function to every element of a matrix. So I can do all of this. I can start to write the code for a neural network library. Okay, we have now arrived at what is sort of the end of this video. I'm going to pause and check and see what all the wonderful, nice people who are generous enough to follow this along live have corrected me, and see if I need to come back and offer any corrections or answer any questions. I'll be right back. Would it be clear to write out the equation for the output layer as well? Shouldn't be too difficult with just 2 weights. That's not a bad idea. Why don't you add the biases to the weight matrix instead of having an extra matrix? I don't think that would work. So Simon Tiger writes, a bias doesn't have a weight, and that is correct. But I like to think of it, I think the biases are just numbers. They just get added in. But it's the equivalent, if I wanted to, of having another input, right? It's the equivalent of having another input of 1 and then adding another column. And those would be the biases to the weight matrix. So I could do that. Maybe I'll mention that. So instead of, yeah, I could mention that. All right. You were using the same name for both weight matrices. Yes, that's a big problem. Yeah, I meant this to be like, okay, so let me do some of these corrections. Okay, so a couple corrections that I should do is, these are not, I'm being very unclear about this. These are not the same, these are not the same, these are not the same. So this weights here, these are really what I would call like the input to hidden weights. So I'll call this like WIH. The weights from, and you're going to see this kind of variable naming when I start to write the code for this. The weights from input to hidden, and this is really the weights from hidden to output, WHO. So that's one point of clarity that's important. And also, once again, for the biases, these are like the hidden biases, and these are the output biases. Again, I'm kind of, on some level, making up my notation on the fly. I'm sure if you were to read a properly thought out textbook or watch a 3 Blue 1 Brown video, there's some more precise notation. But this is the way I'm thinking about it. Another thing that I'll mention here, which was mentioned, is if, the biases, you can kind of write it as this extra matrix column matrix that you're adding on. But I could have, in fact, also just folded those into here, right? Because if I added another input that's always 1, like I added this diagram here, then I would just have, I'm sorry, not another row, another column, which would be the bias values. So I could actually have B1 and B2 here. I could also express and put the biases in this matrix calculation as well. I like to think of them separately. To each one's own. To each their own. Okay. Wait. Should I say goodbye? I don't know if I should say goodbye now. Just let me check one more time. Superscript is common. That would have been good. Change the O to H. Got it wrong. Change the O equals to H equals. Where? Shoot. No, I'm right. No, I'm wrong. Oh. Oh dear. Oh boy. Oh, erase that. Let's do that again. Oh, that was so sad. Hold on. It's okay. We're going to back up. We're going to do that little addendum to the video again. No one will notice. And then I can use superscript. I can have subscript for the index values, superscript for the... Okay. I totally did that wrong. Still not as bad as last time, yeah. All right. Okay, now let me kind of like let me come back into, okay. All right, so there's definitely a few things wrong or misleading, at least I would say, about this that I've gotten some good comments from. So let's go ahead. Number one is it's very important to realize that these two weight matrices and these two biases are not the same. I wrote them out. I mean, we have the hidden outputs and the outputs output. That's what this is, that's what this is. So the hidden's outputs are actually the weight matrix between the inputs and the hidden. So I could write that as like superscript up here, WIH in a way. This is the hidden's outputs is the weight matrix between the input and the hidden with the matrix product of those inputs. And this weight matrix is the weight matrix between the hidden and the output. HO, or who. So, and you'll actually see as I get into the next video, I'll start using this kind of IH or HO kind of naming in some of the variable stuff. The other thing is these are not the same biases. This is the bias for that's connected with each hidden neuron, and so I could say BH there. And then this is the bias, right, that's connected with, it's just one bias, but it's connected with this output neuron, and so I could put an O here. So that would be more clear about that. Another point of clarification is there is a way to write this without having this, having the bias as part of the weight matrix itself, because there's no reason why I couldn't just consider the bias, like I said, as an extra input that always comes in with a value of 1. And then what I would need to do, where's my eraser, is I would need to add a fourth column here, right? Because this weight matrix would have all of these connections, 1, 3, and 2, 3. And then there would be the bias values, bias 1 and bias 2. So if you see this, this would actually end up, now I could just add in over here, if I followed through with this math, plus B1 plus B2. Because it would be multiplied by 1, which would just be that bias value. So that's an important thing to say. Have I possibly finished this video? Some people were asking, why don't I write out the matrix formula for this? No, you know what? Maybe I should make this an exercise for you, and I can maybe include a little link to a JPEG or something that has it. But could you do this same exact diagram for the calculations that flow once the outputs come out of here through this layer? So let me just, this might be the end. Just give me a second. I'm going to check, see if there's any last comments or questions or important corrections. I'll be right back. All right. All right. I'm looking. Anybody else have anything else? It's all wrong. Okay. Better than last time, at least. This is what it's going to say on my tombstone. Better than last time, at least. Or that's what's on the big poster about the coding train. It's a little bit better than last time. It's okay. 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 It's important to mention the weight of the bias changes. Yes. With the bias baked into the matrix, do you still add the bias into other formulas? Feels like the chat is more important than usual for this video. Just name the video Chaos. New t-shirts, better than last time at least, yeah. Didn't we have this great t-shirt idea? What was that great t-shirt idea? It was something like, I watched your YouTube channel and all I got was this lousy, I watched all of your neural network matrix math videos and all I got was this lousy 0.27 something. Yeah, back propagation is going to come on Friday. I will not be doing that today. No, not today. All right, so I think I'm going to wrap this up. Okay, that in fact was the end. Thank you for watching this video. I should have saved something wise. Okay, that in fact was the end. Thank you for watching this video. I do want to mention that in the chat are a lot of really useful and important points and comments about how my notation and superscript versus subscript and I or J, this is not perhaps the most conventional or correct notation. So I apologize for that. Feel free to leave comments in the comments section, particularly good ones. If there's a really one that sums it up all perfectly, I'll pin it right to the top. But the point of this was for me to kind of get through the basics of this. I am now going to, in the next video, actually implement this in code. And once I've done that, we'll be ready to then look at the learning algorithm, the training algorithm, this thing called backpropagation, implement that in code, then the neural network will be complete and we can actually use it to solve something, I hope. So see you in a future video. Thank you. Acting. All right. Now here's the thing. I also need to, was I not in the right screen there? No, I was. All right. All right. I'm in the wrong screen now. Okay. So what I need to do now is record a brief introduction to the next video. See, I think I already did the coding part, and I think the coding part is fine to go forward. Without me doing it again. Oh, I should probably just do it again. Right? Mathieu, are you still watching? The problem is I don't remember what I did. Let me take a look at that while I'm here.
A lot of time.
This is wildly different. Do it again, please. I think I should do, I was excited for my, it was very short, but it was fun. All right, I'm gonna leave all options on the table. Okay, first, I'm gonna just record a short intro into this video that explains why it doesn't match up. Then I'm gonna redo it again. Yeah, no, there's not gonna be any new stuff that's happening today. I don't have the time to start doing the gradient descent and all of that because and is the matrix, I gotta talk about the code. I have not really published the code. I gotta think about how to do that. Give me a second, everybody. So remind me about that. All right. Hello. You're about to watch a video where I implement what I just did in the last video with code. The only thing is, in the last video, I look like this. And in the video you're about to watch, it's Wilderness Dan who was in the wilderness reading textbooks about deep learning. And also the whiteboard's not gonna match exactly. This is the whiteboard that I just completed where I really kind of worked on and figured out all of the notation in this diagram. And then when I start to implement the code, I might refer to this whiteboard, which looks a little different. I gotta just redo the video. You're never gonna see this. This is no good. We're gonna redo the video. I mean, let me just do it again.
You're like a crazy person.
I mean, the only thing that I'm sad about now is I don't get to have a nice shot of me like this. I'm gonna talk about this anyway. I'm going to talk about this anyway, because people should know. The world should know what I went through to try to get these videos out. But let me first go back to, I have to take stuff out of the code. Right? I don't think there's anything, I think I made the from array function in that. Does anybody remember? I think I made the from array function in that second video, right? So I think this has to go. And the to array function, I think. Those are the only two. Does anybody have a solid memory of this? I think the matrix, so this I'm going to recode everything here, right? This I'm going to completely rewrite the code. And yeah, Simon, so I did it all as one live stream, but my intention is to chop it up into several different videos. So even though it was there, so yeah, the two array functions weren't there. Okay, thank you. So I'm going to go and put this somewhere. Just like make a backup of it. Put it somewhere. Then I'm going to, what I'm going to do here is
I spent a lot of time looking like a crazy person trying to write out and understand the feedforward algorithm for a neural network, a simple matrix.
oh yeah.
Get essentially random output. I do need to do the next part, which is not going to be easy, which is train the neural network, tuning all the weights and biases, so that the neural network learns what are the optimal weights and biases to output the correct, well, correct is kind of a weird word to use here, but the sort of desired output based on some trained data. So gotta get to all that training stuff later, but here I just want to get the feed-forward algorithm to work. Off I go. All right, so here's the fun. I didn't realize I made all these matrix videos to make my little
All right, so this is what I had. So let me just go back now. Yep. Oh, right, I made the joke, the t-shirt thing. That was at this video, yeah. Okay. So it said lots of matrix math and return guess. Okay, so that's what was here. This did not have the from array or to array functions. And so I will also put that in the little backup file that I made just in case, just to have those there. And there we go. Okay. Yes, I'll make this the same joke. Yes, yes. Don't worry. I apologize. I will make the same joke. It will not be as good because it won't be spontaneous. I think you changed the randomized function too. Thank you. That is such a good catch. It was like, it was something like this, right? Because it was giving me random numbers between 0 and 10. That I recall as well. Thank you. All right, I think I'm ready to go. Oh, no. Oh, I had the perfect freeze frame.
just where matrix object and an output layer. I just can't bring myself to do that because I'm so used to array indices as starting from 0. But I do think you're right. I think I spent a lot of time looking like a crazy person.
Okay, there we go. All right. Oh, thank you, Simon. That's a pretty good idea, actually. I do like that improvement for the to array thing. The only thing is if it won't work if it's full. Okay. Okay. All right, yes, I'm very good at picking the right freeze frame. All right. Hello, it's time I admit something to you, which is that I actually recorded a live session where I tried to explain all of this feed-forward algorithm thing a while back when and apparently this like wilderness hair, Sorry, I'm workshopping my wilderness joke. Can you let me do that again? Because my wilderness joke is kind of important. All right, it's got to make it in there, wilderness Dan. Okay. I have to do a 5-mile training run for the New York City Half Marathon today. I got to get going. We'll talk about that too in a second. All right. Here, I'm gonna start over here. Okay, so if you watched the previous video, first of all, thank you. Oh my God. Camera went off. Good timing. Hello. Now, if you watched the previous video, hey, thank you. I hope you're not too mad at me, and I didn't file too many complaints in the comments there. But in the previous video, I talked through the feed-forward algorithm. I attempted to map it and graph it. I attempted to get all the indices right, to explain why we use matrix math for it, all that sort of stuff. Now, at some point we got to get to the interesting part, which is actually to use the neural network for something. It's taking me a while to get there. I will get there. But I absolutely need to confess, if you thought that was bad, I actually, Wilderness Dan over here, tried in a live stream previously to go through all this and got all the index values and everything wrong. It was so bad I couldn't even get it together to turn it into an actual tutorial video that would make it into the playlist. But it does exist if you're interested. I got a haircut, seemed to fix a lot of things. I look like a much more professional person. You can go back and watch that those previous attempts. So, and I've actually done, so this is my second try. I'm just being honest here. All right, so what is it that I want to do, in this particular video? We can close all this stuff. What I want to do is, I have a matrix class that I've developed. I have a neural network class that I've developed. What I want to do is, I want to be able to write code like the following. Timeout, pause. I just realized I forgot to delete this. I want to be able to write code like the following. I want to be able to go into my P5.js sketch or any JavaScript program and say something like, let NN equal a new neural network. Maybe I want to solve XOR. So I want to have two inputs. I just want to have two hidden nodes and one output. So I want to make a neural network object and I want to give it an architecture. Then I want to do something like I'm going to make an input, like I want to send in true, false, 1, 0. I want to be able to say let output equal neural network feed forward that input. And then I want to say console log output. So this is the code, this is what I want to be able to do. I want to be able to use the neural network on a kind of higher level. And once I can do that, then I can have inputs that are all different kinds of things, whether I'm doing some data science or some kind of learn to play Flappy Bird or whatever it is that I'm doing. Okay, so let's do this. What I have so far here is just, I have that feed forward function. It takes an input and returns that guess. Now, there's no code there. I need to fill in the code, all that matrix math. I need to take everything that I have here and I need to put that all into here. So how do I do that? All right, well, my neural network needs some more stuff. For example, all that it has right now is the number of input nodes, which is I just sent in 2, the number of hidden nodes I sent in 2, and the number of output nodes I sent in 1. Well, what I need is I need to keep track of those weights, right? I need to have weights. And what do I need to have weights between? We need to have the weights between input and hidden, and the weights between hidden and output. So those we've established are matrices. Weights between input and hidden is a new matrix. And now it has a certain number of rows and columns. It has a certain number of columns based on the number of inputs, and rows based on the number of hidden nodes. So we're going to say it has this dot hidden nodes is its number of rows, and this dot input nodes is its number of columns. So that's one weight matrix. And another weight matrix is between hidden and output, and that's going to have the number of rows, which is the number of output nodes, and the number of columns is the number of hidden nodes. So I've created these weight matrices. Now, we have an interesting question. When we create a neural network, how do we pick the weights? Again, the whole point of this is we need to have some interesting, wonderful, exciting, complicated, weird algorithm for tuning the weights, for finding the optimal weights for whatever type of application we're trying to build. But to start, we just want to give it random weights. And this is a whole field of research dedicated to figuring out like good ways to seed a neural network with good kind of beginning weights so that you can get the optimal weights more easily, blah, blah, blah. But for us right now, I just want to give it random weights. So I can actually just say we've already built a randomized function into the matrix library. So I can say randomize. So this will randomize the weights. And actually, though, if you recall, I was reminded by this in the chat that my randomized function for some of my demonstrations, I was actually picking a number between 0 and 10. And it would make much more sense to get a random number between maybe -1 and 1 to start at the weight. So I could take math.random, which is 0 to 1, multiply it by 2, subtract 1, and I've got a random value between -1 and 1. OK, so we're doing well. What else do I need? I should probably keep track of the bias, the hidden bias and the output bias. Again, as we saw when I was sort of talking about it, could put that into the matrices, but I'm going to keep track of that separately. It's a little easier for me. So I'm going to say this dot bias hidden equals a new matrix that has, how many biases do I have? I have, based on the number of hidden nodes, right. Those are the rows, and then one column. Is it? Yeah. Because it's a one column vector. And the bias for the output is based on how many output nodes. So for I need a bias value for every node in every layer. So I need 2 bias values for each hidden node and 1 bias value for the single output node. But again, my neural network library allows me to create neural networks with any number of hidden nodes, any number of inputs, any number of outputs. It just has these 2 layers and the inputs, but so at some point it might be worth expanding it so I got multiple hidden layers, that sort of thing, but this is going to work fine for now. Okay, so what else do I need now? There's something we're missing. So for example, let's just, what am I feeding in here? Feed forward input. This is just an array. But technically, in order for me to be able to do the first stop, right? The first thing that I want to do is I want to say this dot hidden. I'm going to make this let hidden. This will be the output, right? I want to compute the output of the hidden nodes. That's going to be a one-dimensional, one-column matrix. That is going to be the matrix product between the input and this, and the weights, and the weight matrix between, and actually I have to say the weights first, sorry. The weights, remember the order in matrix multiplication really matters. The weights input hidden with that input. Then I'm going to say hidden dot add this dot bias. So I do the matrix product of the inputs and the weights, then I add in the bias, and then I'm going to do activation function. I won't do that just yet. But even this is no good so far. This is no good so far because this input, what does this matrix multiply function expect? Matrix multiply in my library expects 2 matrix objects. And this, the way I've written my sketch, is I just made the inputs an array, which is an incredibly convenient thing to do. I don't want to make my end users have to figure out, they just want to be able to send the inputs in a simple array. So one thing that I should do here, I mean I could test, I could check if it's already an instance of a matrix, I could skip it. But what I want to do is I want to say, I'm going to call this input array. I want to say inputs equals matrix from array, input array. And the reason why I'm writing this out is because I've thought of this already. I need to be able to make a matrix object from that array. So I want to be able to have a matrix object so that my matrix multiply function will work. And I could create a different constructor that takes an array, but I think what would make sense is for me to add, right up here in the beginning, right, a static function that's called from array. It takes an array. And what I want to do here is I want to say let m equal a new matrix that has a number of rows based on the array's length and one column. Right? I want to create a matrix that looks like this. It has a number of rows based on the array's length and one column. And then all I need to do is say for let I equal 0, I is less than array dot length I plus plus, and I'm going to say data, m dot data index I index 0 equals array index I, and then return m. So this is just, again, I'm sure lots of you could probably think of some type of array functionality that I could use really easily, but this is creating that matrix and then putting the input into it. So just to be sure about this, let me say m.print. Right, let's take a look, and I'm going to just hold on, edit point for a second. I don't know why this computer went to sleep. All these notifications. All right. Okay. Sorry, I'm not running anything, so I just need a second here. No, I want to go to desktop. I lost my... okay. No, I changed it. It was this.matrix. I've since changed it to this.data. So some of you missed a key point where I did that. Yep, okay. Okay, let me just make sure this works. So I have some errors here. Oh, that actually nicely printed something out for me that I didn't realize it would. So what I want to do is I want to say let array equal a 1, 0, negative 5. And then I want to say matrix dot from array. And we should see, there we go. We've got a column, a single column matrix, 1, 0, negative 5. So that function is working the way that I hoped it would. So I can take out this debugging and I can keep this in here. And now if I go back to this code, I can say, okay, we get an input array. We turn that into an input matrix. And then, this needs an S here, we multiply, we do the matrix product of the inputs with the weights, we add in the bias. Only one more step left to go. We need to do the activation function. So, we need the sigmoid function. Well, it so happens that there isn't a magical sigmoid function that exists in JavaScript. However, there is in the math library a function called exp, JavaScript math. Let's find this documentation page. This exp, Euler's number, or also known as Napier's constant, does for us e to the x. So I can write my own sigmoid function. So I can just, and at some point I probably will allow the neural network library to use different activation functions. But right now I'm just globally going to write a function called sigmoid. It's going to take one input x, and it is going to return 1 divided by 1 plus math.exp negative x. Somebody fact check for me, but I believe that is the sigmoid function. And so the wonderful thing now is once I've received the inputs, once I've done the matrix product of the weights and the inputs, once I've added in the bias, I can generate the outputs with the activation function just by saying hidden.map sigmoid. If you recall, I wrote into my matrix library a function called map, which just allows me to apply any arbitrary function to every element of that matrix. So there we go. Now we're done. So this is all the code for generating the hidden outputs. And this is the activation function. Now, where are we in the diagram? We've got the inputs. We did the matrix product. We added in the biases. We passed through the activation function. Now those outputs are coming in here. So what do we need to do now? Take those hidden outputs and do the matrix product with these weights. So we're going to do exactly that same thing. We're going to say let output equal matrix.multiply this dot weights. Now I need the weights between the hidden and the output, HO. I need the hidden outputs, which is I'm just calling hidden. Then I need to add in those output biases. Did I call it bias O? Yes. I need to, oh, and by the way, I just realized I never gave these any initial values, so it would make sense for me to also randomize these. So I'm going to randomize those biases. So now I've got the weights times the matrix product of the weights and the hidden outputs. I'm added in the bias, and then output.map sigmoid, and guess what? Return output. That's all I want. That's done. That's the last piece. I want to send in the inputs, right? I'm over here, sorry. In my actual code, I want to be able to send in the inputs and then read out the output. But here's the thing. I sent in the inputs as a simple array and then internally converted that into a matrix so I could do all the math properly. Now, before I get the outputs back, I don't actually want to send out a matrix. It's going to be simpler if I just send out those outputs as an array. So much like I wrote that from array function, I am going to create a function called toArray. And that doesn't need to be static because I'm going to take any given matrix object and return an array. Now, there are some, I could probably transpose it and do some fancy way or use the slice function. Again, I'm going to do this just in a way that I know will work. We can always refactor this later. In the end, I'm going to refactor all this using somebody else's matrix library anyway. So let me think about how I would do this. First, I want to make an array. I'll make it empty. And then really all I want to do is I want to loop through every element of the array, every element of the matrix. And what I want to do is I just want to say array.push every element of the matrix and say return array. So this would actually take any two-dimensional matrix and flatten it to a one-dimensional array. The question is, though, one thing we should ask ourselves here, is it appropriate to have the columns as the inner loop? So if I think about it, if I wanted to take, I mean, obviously it doesn't matter if it's this matrix, because I just want to take all these and put it into an array. But if it's this, if I want to take like this array and flatten it, do I want to go do, or do I want to go do? I think I want to go this way. I got distracted by my own singing of, that's the iteration song is just All right, sorry, I'll get back to this, I apologize. I think I want to iterate through the columns on the inner loop, which it looks like that's what I'm doing. So I'm going to keep it this way, except for, yeah, okay. So I'm going to keep it this way, and I'm going to say here now in the neural network, I can say return output.toArray. Okay, everyone. This is it. This is the whole feed-forward algorithm. This is receiving the inputs, generating the hidden outputs. Now, generating the output, and then sending it back to the caller. All right, so this is the whole algorithm. This is like layer 1 and layer 2, the hidden layer, the output layer. What have I missed? We'll see. Okay. All right, let's look at this now. Yeah, it's probably no need to randomize the biases, but that's I did it anyway. Okay, hold on. Time out. Okay, what do we do now? Let's try running the code. I mean, it's absurd, but because this does nothing, but let's just run this. Let's just see, can I create a neural network, give it some arbitrary input, and get some output? Can I get it with no mistakes? It seems very unlikely that I'm going to have no mistakes. And this is a reason why I shouldn't use my drum roll effect, but I'm going to do it anyway. Okay, here we go. Let's run this code. Ah, oh my God! It worked the first time. Now here's the thing. It worked is the strange thing to say, because really I didn't get any errors. And probably the only reason I didn't get any errors because this is actually my second try of building this out. And you might be wondering like, oh, okay, so I just watched like 2.5 hours of like 8 videos in a row about matrices and neural networks. And you just went for 0.593107. So, you know, and we should probably get a t-shirt that says, I watched all your YouTube videos and all I got was 0.5931. It was funnier when it was like a low, I made this joke before in the previous attempt and it was a lower number. Somehow 0.27 is a funnier number. Like, right? Like what's a funny, I feel like that's pretty good. I feel like, I think it's got to even be lower. The lower the number is, the funnier. There we go. See, now it's funny. Oh, wait a second. Okay, so the thing is, we got to start testing this. We've got to come up with this. We're getting close. What I want to do, probably the first thing I'll do, it's not that interesting, but at least allow us to test whether this code works, is can I train it to learn an AND operation, an OR operation, or XOR, exclusive OR, which is one that I've talked about that can't be solved with a single perceptron. So can I feed it in 1, 0 and train it to get the number 1 out? Can I feed it in 0, 1, train it to get the number 1 out? But if I give it 0, 0, 1, 1, I get the number 0 out. So I need to attempt that. But I am missing a lot of functionality from this neural network class. I have this feedforward algorithm function. Now what I need is to write a function called train. And what I'm going to do with the train function is I'm going to give it some inputs and then I'm going to give it a known answer. So the idea here is like with feedforward, I'm really just saying take these inputs and give me an output. With training, I'm going to say take these inputs that I have a known labeled answer to and do something to yourself based on that. And that's what I'll start getting to in the next video. I have to talk about back propagation and gradient descent. I have talked about this in previous videos. We'll kind of return to that. Then I need to finish implementing this function. And then I'll do a coding challenge where I try to solve XOR and do like a simple digit recognition or something with this particular neural network library. Okay, thanks for watching. I'm going through this. I'm trying it out. I'm seeing if I can make this neural network stuff happen. I'm doing if I'm being honest, it's a B minus. I think it's a B minus. But all things will come eventually. So thanks for watching, and as always, I don't know, subscribe, like, that helps supposedly, and because then YouTube's neural network, I'm just copying 3 Blue 1 Brown's joke at this point. You should watch 3 Blue 1 Brown's videos. They're really good, I learned so much just from like watching those. And so I'll be back in the next video at some point. Thank you. All right. Mathieu, I hope I saved you a lot of editing time. And save, I think we're good. I think we're good. I think we're good for today. Did I forget to apply the weights to the biases? I don't think I did. I think I'm okay. I think I did everything. Did I miss anything important? Brian, I've been waiting for back propagation. Oh, why use sigmoid and not relu? It's a French activation function from what I understand. Good question. I mean, I should use it, but I'm not prepared to because I just kind of want to go through what the other... let me make sure I talk about it in the next video, though. But yeah, I should come back to that. Okay. It is 3:45. One of the reasons why I have to leave is I got to make it home, but I'm also, I guess I'll mention this here for those of you who are watching. I am training for the New York City Half Marathon, which I'm doing a fundraiser for. Crowd Rise. Wonderful organization, Lower East Side Girls Club. If you liked watching this live stream today and feel like donating, I am, here we go. You have to do it through my page, otherwise I won't get the credit. It's very important. Hold on, I'm not here. Team, see more. Daniel Schiffman. Okay, here we are. The Lower East Side Girls Club is a wonderful organization that does after-school programs. They have a great makerspace. They have a planetarium. They do wonderful stuff with code stuff. Some of my students have done workshops over there. I've hung out over there. It's a wonderful location, place, not-for-profit on the Lower East Side. If you feel so inclined, I am fundraising for them and running the New York City Half Marathon, which I hope to do in under 2 hours. I have run a half marathon in under 2 hours before. It was like 1 hour and 59 minutes. So I'm just going to plug this for a second for any of you who are watching here. Thank you, Alka, for putting that link in the chat. Okay, I just wanted to mention that since I'm not promoting anything else today, I will promote that. So yes, thank you. That's a good comment. All right, so thanks everyone for tuning in. I should be back on Friday at the regular time. My intention on Friday, if I am so lucky, is to get all the way through solving XOR. So, simple goals. So I want to do the back propagation step, add that to the library, and then I just want to make the XOR and visualize that. You know, there's maybe do some visualize the network. I don't know. Do some stuff with it. So probably XOR and MNIST if I can. Okay. Whoops. Was that link no good? Thanks for trying, Alka. I can paste it in. Hold on. Because I am actually in the chat as well. There we go. Okay. And whoa, I'm behind here. All right. Okay. So this is it for today. It is 3:48. I gotta go. So thank you everyone for watching. Send me your feedback at Schiffman on Twitter. Like, subscribe, all that nonsense. And yeah, I'll be back on Friday. If somebody can, by the way, find this song for me, I think I found it at one point. I think it was on Free Music Archive. And it had the word rainbow in it. But also, it could have been that I searched for it on, I don't think so. No, I think it was Free Music Archive. Could have been on SoundCloud, I'm not sure. All right. Yes, ReLU stands for Rectified Linear Unit. That is correct. All right. My link didn't work either? Ugh. Hold on. Let me at least show you what the link is. I'll take while I'm wasting time doing this, I'll take a few questions from the chat. All right, let me take a couple questions in the chat. When will the code? Ah, yes, good question. So, yeah, okay, so a couple questions. So Taco Dude asks, why don't you make it so you can have more than one hidden layer? I absolutely should do that. I'm starting simple, building things out. At some point, I don't know how far it makes sense for me to go with this neural network library, because eventually I'm going to try to replace most of this with this deep learn JS thing, but c'est la vie. But people are asking about what to do about the code. So here's the thing. The code for this ostensibly is on github.com/Schiffman neural network p5. this, you can see like, oh look, here's the neural network code. Wait, that looks kind of the same but kind of different. Here's some matrix.js. Oh boy, it looks pretty different. It's not even ES6. So I made this a long time ago, not that long ago. Last commit was somehow 5 days ago, but really it's like six months ago or so that I like last did anything about this. So I made this a long time ago. Use a URL shortener. Okay, you know, people will find, you'll find the, tweet at me, I'll send you the, I don't know how many of you are really gonna donate, so I don't think I need to waste too much time about the URL. But, hold on a sec. So this is the code. So I want to update this and have this code match what I'm building. But I'm also happy to accept pull requests here to optimize and fix this up. So I think what I probably should do is have the raw code from the examples go in Rainbow code, and it would probably go under, I would say, if anyone wants to help me with this, courses, nature of code, and it would be a videos started numbering with 10, or intelligence and learning, session 4, I don't know, this never really got anywhere. So maybe nature of code, it should be like there should be a subfolder here that has the code that goes along in steps with each and every video precisely, and then a sort of finished version of it that's maybe a bit more optimized would end up here in this library. So I would gladly accept any pull requests and help in that direction. That's kind of what I'm thinking of by right now. Simon in the Slack channel for Patreon subscribers, asked, when are you going to do k-means? It was on my list and I kind of never got to it, so I don't know. I'm going to have to come back to that at some point. Read random numbers. Someone's telling me somebody just donated. Oh my goodness. Well, I'm definitely, whoever just donated that, I have to give you a massive thank you. That is so kind and nice of you. Topher J. Thank you so much, Topher J. These random numbers I'm about to read are dedicated to Topher J. 36,453, 14,928, 23,931, 32,095, 30,757, 56,802, 34,885, 87,169, 11,386, and 98,614. Breaking news, breaking news. Coding train, breaking news. Someday I'll have that sound effect. I'm being told that maybe freemusicarchive.org/music/the_Colombians just like a rainbow. You're only hearing this through my mic. But yep, that's definitely it. There we go. Thank you very much. I need to step up my music game. It's so tricky with sort of copyright stuff, but I kind of like Scott Joplin would be good, I think, for me, like a kind of Keystone Cops like aesthetic. Maple Leaf Rag would probably be good. So anyway, yes. Oh, okay. So green thing on my desk. What's the green thing on my desk? I mean, this thing. It's just another laptop. It's where I have a Slack chat going. I hope I didn't just violate anybody's privacy in the Slack chat. Okay. Will you ever make a neural network that can play a game that you can make live for a coding challenge? Yes. That's kind of my goal. It's raining tacos from out of the sky, tacos. Why do I know that song? Tacos. All right, I've really got to go. Thanks, everyone. Burger Bob, I'm very sorry to say that I'm now finished with the live stream and I will be back on Friday. Well, how long was this today? 2 hours? Something like that. All right. Thanks for watching. Mwah! And see you next time. Yes, Elliot, chill. I will return to steering behaviors at some point.